to start what will almost surely be our last unit of the semester based on the time. This is random matrix theory. So this builds very nicely off of the stuff we've been doing on L functions and zeros of zeta functions. The subject actually began probably in the early 1900s with an article by Wishart in like one of the biostats journals. These matrices, appeared in certain statistical applications. There's still a huge amount of statistics that's being done that depends on properties of random matrices. The subject really got going in the 1950s and 1960s when nuclear physicists were trying to understand the structure of heavy nuclei. And so in fact, I was fortunate enough to be trained by physicists including Frank Ferk at Yale, who was one of the original experimentalists gathering the data. And they had on the order between 100 and maybe 1,000 data points. Nowadays, if you're looking at zeros of L functions, you can generate millions to billions very easily. I think I told you when I was a college student, I used to have the library computers calculating things for me all over the weekend. And as long as I got in by 9 a.m. Monday morning, my bosses didn't mind. And it would take me maybe an hour or two to just redo everything I did in several months as an undergraduate. The algorithms and the technology have gotten much better. But this is a real question. When you have a small amount of data, what kind of conjectures can you make? Which ones are reasonable? So the basic premise is we want to understand how an atom works. It turns out in quantum mechanics, you can reduce all of quantum mechanics to the following equation. H is the Hamiltonian, Cn is the energy eigenstate, En is the eigenvalue. And you have this kind of eigenvalue equation. The only reason that this is not taught in a standard linear algebra class, and I know some of you have heard me give this lecture before, is that H is infinite by infinite and we don't know any entries. Other than that, this could go into a standard linear algebra class. Talk about diagonalizing matrices. Normally you need to know things like the size of the matrix, the entries of the matrix. These things kind of help when you're trying to diagonalize the matrix. What can you do if you don't know that? So this is a change in perspective. And again, there aren't that many times when we have massive changes of perspective. These are the moments in the development of mathematics and physics that you really want to hop on and think, who made these insights? Who changed what we're looking at and why? What inspired them? Most of us are brick builders. I'm, for the most part, a brick builder. It's a worthy profession, but there's lots of people who can build the bricks. It's coming up with a whole new set of things to study. And Wigner's great insight was that the randomness of what's going on actually helps. If you think about what's going on, if you have hydrogen, one atom, one electron, we'll assume it's not deuterium, so there's no neutron. It's not so bad. As things get complicated, even once you get to helium, it becomes very hard. I don't think we have good formulas for what goes on for helium. By the time you get to uranium, with over 90 protons, over 200 protons and neutrons interacting with a far more complicated interactive force than gravity, it's a nightmare to write down what's going on. Wigner's great insight was this helps us, that there's so much randomness that things basically cancel out. And the idea is when you're trying to calculate what's going on, just choose a matrix at random, plop down the matrix, look at what goes on, and then choose another matrix at random, and plop it down, and then just average over the space of matrices. So we need to put a measure on the space of matrices. This is where the number theorists and the random matrix theorists differ, although for many years they were the same. I think now the random matrix theorists have all, for the most part, agreed, but there is still some what I'll call classical random matrix theory that's being done. One notion is to say, well, I have a matrix. Maybe because of physical grounds, I have some kind of constraints on the matrix. Maybe H is real symmetric. All right, well, if the matrix is real symmetric, once I specify the main diagonal and once I specify the upper triangular part, then I get the lower triangular part by symmetry. So I would have to specify, all these entries and everything else would be determined. So specify A sub ij with 1 less than equal to ij less than equal to n. And the simplest thing to do is to assume the IID, independent, identically distributed random variables. So I'm assuming everybody's comfortable with the basic material from chapter 8. Mean 0, variance 1, and frequently we'll assume finite higher moments. No Cauchy distribution, although one of the best undergraduate projects I ever did was looking at what happens when you put in the Cauchy distribution. So this is one way to go, but it should be leaving you with a very specific question. So I'm choosing my matrix elements independently from a fixed probability distribution P with mean 0, variance 1, finite height moments. What do you want to know?
What distribution?
What distribution, right? Well, the way I've set this up, I can use any distribution. The finite higher moments is just to make sure that things converge. The difficulty is there's nothing here that tells you initially what distribution to use. This has led number theorists to suggest that this is not necessarily the right model, that what we should do is we should look at classical compact groups, subgroups of unitary matrices. And so I'm not going to go into too much detail here, but there's a natural measure associated to unitary matrices called Haar measure. And it allows you to choose the matrices at random with respect to this Haar measure. These matrices form a compact group. You can normalize it so it's a probability space. If you think of a unitary matrix, so UN, these are n by n, and UHU equals UH is the identity. So what this means is if I take the complex conjugate transpose, that's what the H means, the Hermitian conjugate, and I take the matrix product like this, I get the identity. Well, this tells me that the absolute value, the sum of the absolute value squareds of anything, the norm of anything in any row or column is 1. So this tells me I live inside a very finite region. And if I live inside a finite region, not surprising, I can put on a nice probability measure. And it turns out we can do one that respects the group structure. Okay, that's the whole point of the Haar measure. We can put on a nice probability measure that respects the fact that we have a group structure. We could, of course, go back to this situation, and in this situation, we could talk about different P's. The question is which P to use. And if there's a question, well, why not use all of them? And see how sensitive are your results to the choice of probability distribution. Now, the question is, which one actually models the world? Is it the classical compact groups? Is it a fixed probability distribution P? And if so, which P? If you had to guess, what P would you choose? Gaussian. Why? Most things are Gaussian. We've got things that are large. Randomness is going on. How the hell could it be anything other than a Gaussian? Right? So there's at least an intrinsic reason why you might expect it to be a Gaussian. It turns out there's a very natural reason to choose P to be a Gaussian. And I go through the calculation in the book. This requires us to talk a little bit about the very basics of linear algebra. This is always dangerous in seeing how much people remember from their linear algebra. Yeah, so I'll try to face the board and not look at the class. Okay? Let's say I give you a matrix A. How do you think of the matrix?
A transformation.
It's a transformation, okay? Excellent. So it maps some space, vector space V, to vector space V. If I were to write down a matrix, 1, 2, 3, 5, I'll do a Fibonacci matrix. Is this a transformation? Yes. And so for this, it is a transformation, but it's more than just a generic transformation. It's a transformation with a basis attached to it. So I can only write it down like this if I choose a basis. If I choose a basis, I can write it down. But in general, I do not know what it's going to look like. Different matrices will look very different in different bases. Have we done the equation of an ellipse in this class? All right, so if I wanted to do an ellipse, If I draw the ellipse like this, you should be somewhat happy, right? This is the standard way of drawing an ellipse. If I draw an ellipse like this and ask you to write down the equation of the ellipse, this is not as much fun. But I claim if you can do this, you can do this, right? All you need to be able to do is just go like this, and it's no problem. You choose a new basis. I'll shade it in so it now goes to the origin. And we draw it like this. We'll call this U. We'll call this V. We'll call this X. We'll call this Y. In the UV basis, this is now a really nice equation. So the way you would write down an equation here, this is x over a squared plus y over b squared equals 1. You can also write this in terms of a matrix form. Let's see, 1 over a squared, 1 over b squared, 0, 0, xy, and that's xy transpose. If I write it down like this is my equation of an ellipse. How many of you have seen this way of writing an ellipse? Okay, about half. Okay, this is an equivalent way of writing down the equation of an ellipse. Well, I can now write that equation in the UV basis, and I can represent UV as some rotation matrix applied to xy. So in the UV basis, I would get UV 1 over a squared, 1 over b squared UV. And since UV is xy rotated, I can now write xy. I can now represent this in terms of xy. I just substitute in. And what I'll get is I'll get xy r theta transpose, I think 1 over a squared, 1 over b squared, r of theta xy, and that's my new matrix A. And so this is how you would write down the equation of an ellipse in a more general coordinate, in a more general orientation. We first change coordinates, represent it here, and then change back. And so at the end of the day, we can write it in the xy space without any additional difficulties. This is essentially what all of linear algebra is about. You know, if I had to summarize linear algebra in a sentence, it's choosing the appropriate coordinate system. And depending on which coordinate system you choose, things are going to look differently. Choose the one that makes the calculation look as easy as possible. Okay? What is the goal of a math class? What do we try to do in a math class? As opposed to an economics class. We try to prove things. Okay? I cannot prove the following. I can merely suggest as a possible hypothesis. If there exists a God or a creative force, God or the creative force, the universe probably does not care that we have 10 fingers. Can't prove it, but I don't really think 10 is fundamentally important to the universe. 2, base 2, sure. Maybe base E. But 10, probably not. Geometry in Williamstown is not so bad, right? Root 2 heads east-west. Do you think the universe cares which way we orient our coordinate axes? Should physics look different if we change our coordinate systems? No. And again, this has to become an assumption at some point, but the universe should not care about how we choose our coordinate axes. This has profound consequences in random matrix theory. So we talked about what is a matrix. What is a matrix? It's a transformation. If I write it down like this, I can only write it down like this when I talk about the matrix elements. When I talk about the matrix elements, I'm talking about how it looks when I have a basis. Which basis should we use? Depends on the problem. Doesn't really matter. Well, if I'm choosing my matrix elements at random, I have to have a basis chosen. I don't really care about that basis. When I'm looking at a matrix, if I write down the coordinates, I can focus on the wrong thing. I really care about what is it doing to the eigenvalues, eigenvectors. What are those key directions? I don't really care what it actually looks like. And so when we talk about how the matrix looks, when we talk about choosing everything at random, it's easy to focus on the wrong thing. I want to choose a matrix. I want to choose the probability so that when I look at the matrices, the probability of a matrix doesn't depend on, say, the basis I'm using. Now, are some bases better than others? We'd love orthonormal bases, right? Where we have mutually orthogonal directions and all the vectors have length 1. Let's not do something silly and say 1 unit here, 15 units here, and at a strange angle like this. Yes, we can use that as a basis. That's not a natural basis to use. As much as it pains me as a Bostonian, think of Manhattan. Right? A really good coordinate system. Yeah. All right.
North of West 4th Street, anyway.
As long as you're not going towards like the Lincoln Tunnel or anything like that. So when we're trying to think about what's going on, I want to have some probability of a matrix. And I could also look at maybe B is Q transpose AQ, where I rotate the coordinate system and I change the basis. I would want maybe these probabilities to be equal. Why? Because I'm really talking about the probability I choose a transformation, not the probability I choose a matrix. So talk about the probability we choose a transformation, not a representation. Due to time constraints, we probably won't do the calculation. If memory serves, it's done either in chapter 16 or chapter 17. I think probably chapter 17, where I go through the calculation. It's a standard calculation and shows that if you assume this, it forces your density to be Gaussian. And it's a little bit different on the main diagonal versus off the main diagonal. Why do you think there might be a difference between the main diagonal and any other entry in a real symmetric matrix?
These are symmetric about the main diagonal.
Okay, so you're close. So what's the difference between an element on the main diagonal and an element off the main diagonal?
An element on the main diagonal would appear only once.
Excellent. Whereas anything off the main diagonal by symmetry is going to occur twice. So there's a little bit of an asymmetry between elements on the main diagonal and elements off the main diagonal. So it turns out you get a different Gaussian on the main diagonal as you get off the main diagonal. But fundamentally, it's this insistence on this invariance of probability that if I do a change of basis, we get the same thing. This is what leads to what's called the GOE, the Gaussian orthogonal ensemble. The Gaussian is coming from the fact that at the end of the day, we have Gaussian probabilities. E ensemble is just a fancy way of saying collection of matrices. The O, the orthogonal, is talking about its Gaussian from an orthogonal change of variables. If we do an orthogonal rotation, we will still get the same probabilities. If you think about it from physical grounds, this is a very reasonable assumption to input. And then once you input this, then you can see what are the consequences. And this forces you to get to a certain P, a P that's a Gaussian. Could we still look at other P's? Sure. If we do that, however, different representations of a transformation will have different probabilities of being chosen. Okay? If you think about things in life, depending on how you represent it, you can definitely change your probability of being taken. Right? How many of you have ever watched The Price is Right? Depending on how you dress, you have a much better chance of being called to contestants' row. You can do things to change. You're still the same person. It's still the same transformation, but depending on how I write it, I can see things very differently. Question?
Is there a way of comparing that conclusion to what you get when you use the Haar measure? I'm not even sure what it means to compare.
Yeah.
But just
What you can do is you can ask, what is the distribution of matrix elements from a Haar measure? So do you think it could be Gaussian? So this is a good question. Do you think the matrix elements of, say, the n by n unitary matrices, do you think they can be Gaussianly distributed? You should be able to answer this immediately. And if I'm saying immediate, that gives you a clue as to what the answer is.
No.
No. Why not?
Oh, because they have finite,
It's a compact set, right? The unitary matrices live inside a compact set. So I have no probability of choosing a large matrix element. So you will have a fundamentally different possibility of matrix elements if you do the unitary ensembles than if you do the Gaussian orthogonal ensembles.
And so is there kind of room for agreements, or
but
which model which model is more suitable for which situation?
Well, what's interesting is a lot of times they'll give you the same answer in the limit. If you look at n by n unitary matrices, n goes to infinity. If you look at n by n complex summation matrices, you'll see very similar behavior. And again, one of the reasons is we have to figure out what's the correct scale to study things. And this is a huge part of the beginning of random matrix theory. If I give you a problem, what's the natural scale to look at it? When we're looking at spacings between primes, if I'm around size x, how far is the next prime? Log x. So I really want to talk about how often am I twice the average spacing apart? How often am I half the average spacing apart? These are natural questions to ask. How often do I differ by 2? This is extremely hard. There's been remarkable progress in the last few years. And in fact, right now, some of my friends at a nice workshop at the American Institute of Mathematics talking about new results in bounded gaps between primes. But these are very difficult questions because on the natural scale, you're talking about primes that differ by 0. Even if they're differing by 16, it's still 16 divided by log of x is 0. So in questions like this, while the matrix elements may be bounded, in some sense, when we look at the behavior of them, we're going to see very similar behavior between the two different systems. So the question is, how do we handle stuff like this? So the camera's not swinging again. Turns out that the battery must be completely fully charged, and leaving it in the charger all weekend is not enough. Okay, so the key idea is the method of moments. And it goes as follows. Let's say P is a density. The kth moment, the expected value of xk, where k is a random variable whose density is given by P, is equal to the integral from minus infinity to infinity of x to the k P of x dx. And frequently we'll look at the centered moments. We might look at I think they often put a prime here, and we might look at mu k is the expected value of x minus its mean, the first moment, to the kth power. X minus mu. As long as the mean is finite, this is really not a big deal. This is just renormalizing things. And you could frequently renormalize so that it has standard deviation 1. It's just controlling the fluctuations. There's only two cases when you can't normalize the standard deviation to be 1. What are those two cases? If it's infinite, there's no way to divide by a number and make it finite. And if it's 0, okay. If the standard deviation is 0, I will leave it as an exercise. It is not a hard probability distribution to investigate. All right. If you are in a situation where there is 0 standard deviation, this might lead to a subject called thermostatics. Right? It's not difficult. Right? We will be interested in situations where there is some variation, where there are fluctuations, where things do happen. Okay? The idea is if know all uk, we know p. So the idea is, if I give you a nice probability distribution, if I know its moments, I know its distribution. What do you think? True? Always true? Sometimes true? Never true? Sometimes true. Safest thing to do, right? We will be offering complex analysis again this spring. Complex analysis is a wonderful subject. It's one of the things you really need to do justice over here. The problem is real analysis is too inclusive. It lets too many functions in that have no right being studied. Complex analysis is far more exclusive. Think of it as the country club subject of mathematics. Only the right kinds of functions are let in. Okay? By doing this, complex analysis can say a lot more. And so we are in the horrible situation in real analysis that we can have functions whose Fourier series exist and converge everywhere, but do not agree with the function, except at the origin. So we've talked about this example multiple times this semester. What function am I thinking of? No. Yes. What a difference a reciprocal makes. Right. If you take f of x equals e to the negative 1 over x squared, if x does not equal 0, and 0 if x equals 0, then it turns out, using L'Hopital's rule, you can show all the Taylor coefficients at 0 equals 0. This means if you look at the Taylor series of f, hopefully this is obvious notation, this will be the sum, n goes from 0 to infinity, of the 0th derivative at 0 over n factorial x to the n. This has to agree with the original function when x equals 0, because the first term is f of 0, and every other term has an x in it. It only agrees there. Only agrees at x equals 0. This is quite disappointing. I have a nice function, decays very rapidly, and yet the Taylor series only agrees at the one point where it trivially has to. There's not even a small neighborhood of radius epsilon where you can choose any small epsilon you want as long as it's positive, where we have agreement. What this means is if I give you x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, what function am I thinking of? Yes. And that was the function I was thinking of, 1701 over 24601 e to the negative 1 over x squared. If you look at the Taylor series of these two functions, what can you say? They're identical. You cannot distinguish functions just by looking at their Taylor series. So when we're trying to do the method of moments, if I give you a sequence of moments, it is not always going to uniquely determine a probability distribution. That's horrible. Yes?
Would we consider using the Fourier series for this function?
Well, one of the problems is that this is a function on minus infinity infinity. And so this is a function that fundamentally is decaying, is going off. Although actually what happens is x gets very large. It gets close to 1. So one possibility is you might want to look at the function 1 minus this. And if you look at the function 1 minus this, then it's going to be close to 1 near the origin, and then very rapidly decay to 0. And that might be a more interesting function to look at. There's lots of tweaks you can do with a function like this. But this is telling us that there's going to be some difficulty in trying to understand what's going on. It's not going to be enough to know the moments. We're going to need to have some heavy machinery. So because probability and complex analysis are not prerequisites for this class, I'm going to just calculate moments and then just wave my magic chalk